me know, and we try to elucidate it. And okay, so I will talk about the geography of moduli space of torsion-free sheaves. This was the work of my PhD thesis with a joint work with Marcus Jardine and Alexander Tikhomirov. And let's start. So to begin with, I will denote by this calligraphic M, C1, C2, C3, the Giesecke-Maruyama moduli space of semistable rank 2 sheaves on P3, with first, second, and third Chern class equals to C1, C2, C3, the usual thing. So I put a link, so whenever you see this underline in the letters, later the slide will be available, so you can click and see the PDF of the paper that I am citing. So Maruyama proved in the 70s that this moduli space that we are interested in a projective scheme, and also proved that we have the moduli space of locally free sheaves, which I call B, C1, C2, C3 for bundles. So the moduli space of vector bundles and the moduli space of reflexive sheaves are quasi-projective subschemes of this moduli space. So our goal here will be to understand the geometry of these moduli spaces. What can we say of these schemes? So then a few known results that are understood so far is that the moduli space of vector bundles, naturally we don't have the third Chern class. So we know that for first Chern class equals to 0, this guy is completely understood up to C2 equals 5. And for first Chern class odd, we know that we understood this guy until C2 equals 4. And we also know that the number of reducible components of both moduli spaces grows as C2 grows. And we would like to know if we can characterize the asymptotic behavior of the growth of such reducible components, more or less as we know for the Hilbert scheme of curves, for instance. For reflexive sheaves, these moduli spaces are completely understood up to C2 equals 3 and C3 equals 6. And with odd first Chern class, we know them for C2 equals 3 and C3 equals 7. We also know the reducibility and rationality for some extremal case of Chern classes. When I say extremal, is that because we have an inequality for C3 in terms of C2, and the C3 reached the upper bound, we say that this is the extreme case. But we also don't know general results. And for torsion-free sheaves, we know even less. This guy is understood up to C2 equals 2 and C3 equals 4. But we also know that the number of reducible components of these guys grows, and there are reducible components in this moduli space whose generic element is not locally free. Because, okay, it's obvious that the number of reducible components will grow with C2 because we know that the moduli space of locally free sheaves grows. But it's nice to know that we also have a number of reducible components of purely torsion-free sheaves that also grows. And the reducibility and rationality of some extremal case also is known. So what are we going to do here? First is to provide examples of reducible components in these moduli spaces. So how are we going to do that? So we start with a Corinth sheaf. I will denote by EV the dual of the sheaf E. I guess it's more or less clear for everybody. So I will take a torsion-free sheaf on P3. Then the natural map from E to its double dual is injective. And we can take a short exact sequence of this form E, injects in the double dual, and you can take the quotient, QE, that I'm denoting here. So for rank 2 torsion free sheaf on P3, we always will have this sequence, and this will be the base of we are going to work here. And the first thing that we would like to know is that the support of the sheaf QA, that is the points where the stock of the sheaf QA is different from 0, lies inside the singular set of my sheaf, the points where the x1, the local x1 is different from 0. This will imply then that the support of my sheaf QA is at most one-dimensional. So we have the following definition. If you take a rank 2 torsion-free sheaf on P3, we will say that E has zero-dimensional singularities. If the support of my sheaf is a zero-dimensional subscheme of P3, we will say that E has pure one-dimensional singularities if its support is a pure one-dimensional subscheme. And we will say that E has mixed singularities if its support is a one-dimensional subscheme, but it also contains zero-dimensional subscheme. It also contains some embedded points or points outside the curves. And this definition seems very natural, and it's nice to know that this definition will help us to make a lot of computations. So we will try to give explicit examples of family of sheaves inside this moduli space that could be candidates to reducible components of our moduli space. So I will try here to give an idea how to do it. So how we're going to do that? First, we fix families of subschemes on P3 to play the role of support of my QA, and I will call this sheaves Q. I would consider families of reflexive sheaves on P3 that I'm denoting just here by R, that we're going to be well behaved enough in order to play the role of the double dual of my sheaves. And this well behaved enough is in order to habilitate us to make computations with them. And I will consider also the family of all possible epimorphisms of sheaves from F to Q with my F fixed inside my family R. With these ingredients, I will obtain a short exact sequence. I will take my phi from my epimorphism from F to Q. I consider the kernel of this map. This kernel is a torsion-free sheaf, which I will call elementary transform of F along Q. And these elementary transformations are the main tool that we are going to use in order to build these reducible components that I am saying. So, how we are going to do that? We are going to fix E between -1 or 0, because I want to work with normalized torsion-free sheaves. And I will fix a reducible, I will fix an open subset of my moduli space of torsion-free sheaves, of reflexive sheaves, sorry, with Chern classes E, N, and M. This open will have the property that every sheaf that I take inside it will have the x2 of it equals to 0. So we know that these guys will only have smooth points inside my moduli space of reflexive sheaves. Now, sorry for the long notation and have notation here, but we have no choice in order to explain what I am doing. I will denote by P3S underline 0 to be an open dense subset of S copies of P3 consisting of disjoint unions of S distinct points. So I'm taking inside P3 S copies of P3 different points, and I'm considering the points of all of these distinct points. And for every sheaf, reflexive sheaf inside this module, inside this R star that I took, I can take a PF, a set of the points inside P3 that does not intersect with the singular set of my F. This is possible because the singular set of a reflexive sheaf in P3 is always zero-dimensional. We also have this calligraphic XF to be the set of lines inside this Grassmannian, and this open dense subset of the P3S that such that the line inside the P3 does not intersect the points, the S points, and I don't want the line, neither the line nor the set of points to intersect the singular set of my F. So I'm taking the best possible situation, and I also want my F, when I restrict my sheaf to the line L that I took in the Grassmannian, I want my sheaf to have trivial splitting type on it. We know that when I put everything together by Gravett-Mulich, this set of the sheaf and the set of the line and the points took, as I said before, will be an open dense subset inside the product of my modular space of sheaves, the Grassmannian, and the projective space, S-cop of the projective space. And then this guy here, when I put the zero here, the product of these guys is a smooth and equidimensional scheme, meaning that every point there has the same dimension, dimension of the tangent space. Now, if I take my R to be greater than my E, I will always, then I will fix a triple of a sheaf, a line, and a set S of points. And I consider my sheaf Q, L, S, R to be just the sum of the structural points S with the structural sheaf of my line twisted by R. Then I can construct a morphism from my sheaf F to my sheaf Q that I just defined. So you can see I fixed the F, I fixed the line L and the points S to play the role of the support of my sheaf, and then I defined the sheaf Q. I put this condition R greater or equal than E in order to be sure that I have a morphism from F to my sheaf Q. Now I can consider the vector space of homomorphisms from F to Q, and I can consider my open dense subset of all epimorphisms from F to Q. So this is just following the receipt that I gave you before. I just put this sort of complicated stuff. And then by the construction of we just did before, the group of automorphisms of my sheaf Q acts on this vector space, on this open dense inside this vector space, and we can prove that the action, this open dense subset, and the action of the automorphism group on this open dense subset will give us just a copy of a projective space with a lot of copies of P1. Now, for any morphisms that we take in the from F to my sheaf Q, if we take the kernel of this map as we have defined before, and this will give a stable sheaf, and therefore this will lie in this modular space here, and we can compute the Chern classes just taking the Chern polynomial and making it by hand. So we also can see that two sheaves, if I take two epimorphisms, F and F prime, we'll have that the kernel are isomorphic. If and if, we can find a G on the group of automorphisms of my sheaf Q, making a diagram commute. So we have that phi must be a composition of my G and my phi prime. If I denote the equivalence class of any epimorphism by phi bracket between brackets, and we can consider this scheme, this ugly scheme here, tilde key, in which I'm taking I consider a point inside this guy to be just my sheaf, the equivalence class of my sheaf, reflexive sheaf, and my line and my points defined as they don't intersect. Then this set will be endowed with a structure with a smooth equidimensional scheme. And more importantly, the number of reducible components of this guy will be the same of the number of reducible components of this moduli space of reflexive shift that I took. Since for any point in this Q, the sheaf EX taking the kernel of the epimorphism is stable, and therefore defines a point inside the modular space, we can prove that we have a well-defined modular morphism from this scheme that I just have defined to the modular scheme of to the modular space of reflexive sheaves, just associating to each point the associated sheaf, the associated elementary transform. It's clear that our morphism is embedding because for every point in the image of this map, we can recover the reflexive sheaf just taking the double dual of my sheaf, and we can recover the line and the set of points by taking the support of the quotient, and the morphism is just, the epimorphism is just the natural projection. So indeed, we have produced with these families, reducible families inside the modular space. And then now we consider X with these letters, the closure of this morphism psi inside the modular space. And these the reducible components of my tilde chi, I'm sorry for this, it's not of psi, are reducible families of this modular space. So, so far we have reducible families in order to prove that these are indeed reducible components. We need to prove that for each point inside this guy that lives inside the modular space, we have that the dimension of the tangent space coincides with the dimension of the variety X. And luckily for us, indeed, we can prove this. We can prove this equality, and then we have the first result that says that if I give 5 integers satisfying these properties that I said to you, then this scheme X is equidimensional of that dimension that is written here. And the number of reducible components of this guy is the same as this of the dimension of, and the number of reducible components of X is the same of the number of reducible components of my modular space of reflexive sheaves. I should have put it here that indeed this guy give us reducible components of the modular space, so sorry. The important thing that should remain from this discussion is that when I take a generic sheaf inside these irreducible components, this sheaf should fit into an exact sequence of this form, that this sheaf should embed in double dual V. This double dual, this E double dual should be an element inside the modular space of reflexive sheaves with Chern classes E, N, and M, and the quotient will be the quotient will be isomorphic to the structural sheaf of L twisted by R plus the structural sheaf of S points. So the form of this guy will be important for us in what follows. We also can produce reducible components of sheaves of zero-dimensional singularity sheaves, making a similar construction. And the important thing here is that I will denote these components by T. These components will lie inside the modular space with Chern classes E and M minus 2s. And whenever I take a generic element inside these components, this sheaf will fit into an exact sequence of the following form, where S is a set of distinct points inside P3 that does not meet any of the singular points of my reflexive sheaf. Okay. So I should add that now we have produced examples of sheaves with mixed singularities, with zero-dimensional singularities, and of course, if we don't take any point in the previous construction, we also can produce examples of sheaves with one-dimensional singularities. So we have all, from the definition that I gave in the start of the talk, we have produced examples of reducible components of all three kinds of sheaves, of possible sheaves. So the first application is that in the same way that we have for zero-dimensional, for odd, for first-Chern class even, we have for first-Chern class odd. That is that we have infinitely number of components of sheaves. Whenever the whenever the second Chern class grows, we can have infinitely many. No, sorry, we have a very large number of components with generic point corresponding to sheaves that are zero-dimensional, with zero-dimensional singularities, with sheaves that have mixed singularities, and with sheaves that have one-dimensional singularities, pure one-dimensional singularities. So the result on the existence of reducible components help us to see that this modular space will be very complicated when the second Chern class grows. Unfortunately, this does not give us an asymptotic behavior for the number of reducible components. And we would like to know if these results can help us understand the geometry of the modular space with the small Chern class name. And here I will present the study for the cases. I will fix the first Chern class equal -1, the second Chern class equals 2, and I will make the study for every possible C3. Remember that in the beginning of the talk, I said that the third Chern class respects an inequality, and this inequality make all the possible Chern classes for the second Chern class equals 2 to be 0, 2, and 4. I will begin explaining some numerical invariants. So if we consider a sheaf inside this modular space, we will have that sequence that I just said, because if E is torsion-free, then we can inject into its double dual and consider the quotient. And we have that the first Chern class of the double dual coincides with the first Chern class of my E. We have that the second Chern class of the double dual is equals to the second Chern class minus the degree of the support of my sheaf. And we also have this third equality. These three equalities mean that we have that the Chern classes of the double dual cannot be obtained in function of the Chern class of my sheaf and the degree of the support of QE and the third Chern class of QE. So our approach here will be by brute force. We are going to fix, since we fixed the Chern class of E, we are going to study all the possible cases for these other numbers that are free, meaning the second, the Chern class of our double dual, and the degree of the support in order to make the equality, these three equalities hold. So Chang proved that the modular space of reflexive sheaves with these Chern classes -1, 2, and 4 is reducible with dimension 11. And therefore, the closure of this guy inside the modular space of torsion-free sheaves is an irreducible component. And now we take a point outside the modular space of reflexive sheaves. And since we are assuming that E is inside this modular space, we know that it's semi-stable, but since the first Chern class is minus one, we can prove that E is also stable, Giesecke stable. Once E is stable, we have that the double duo is also stable. And by Bogomolov inequality, we have that the second Chern class of the double duo should be non-negative. And by the second equality that I just showed you, we have that the degree of the support of the QE should be at most 2. And with this, now we study all the possibilities for the degree of the support. If we start with the support with degree 2, we'll have that the C2 of double duo should be 0, since and since the double duo is a stable sheaf, we have that also the third Chern class should be 0. And then we have that the double duo of our sheaf E should be O minus 1 plus O. But this cannot occur since we know that the double duo is stable and this guy is not stable. So we can't have in this situation the degree of the support to be 2. Now, if the degree of the support is 1, then we know that also for the equality that I showed you, that C2 should be also 1, and C3 of our double duo should be also 1. Then we know that our sheaf, our reflexive sheaf, should lie inside this modular space R minus 1, 1, 1. In this situation, we can see that our sheaf QE can be obtained as extension of this structural sheaf of the line twisted by some R, and some maximal zero-dimensional subsheaf of QE supported in S points. And this will imply that the Euler characteristic of our sheaf for every twisted T here is T plus 1 plus R plus S. And computing the Euler characteristic here, we'll have that minus 1 should be minus 2 minus R minus S. We just make the computation assuming that the Euler characteristic of our QE is like the form that I just said. And then we have in the quality that minus R minus S equals to 1. Remember that minus R is the twisted of the sheaf in the structural sheaf of the line. And S is just the number of points in the support. It's the length of my sheaf Z, of my sheaf Z, E here. Now, in order to have an epimorphism from double duo to my sheaf QE, we must have that dr should be greater or equal than minus 1. So if R is minus 1, we have that S equals 0 is the only possibility. Then we just prove that the QE is just the twisted, my structural sheaf of the line twisted by minus 1. This means that we are looking for elementary transformations of F. This is minus 1, 1, 1, sorry, along lines in P3. Now, we want to compute the dimension of the family of sheaves that can be obtained as kernel of epimorphisms from this F to the structural sheaf of the line. But now we don't, we have two situations essentially. If the line does not intersect the singular set of my sheaf F, of my reflexive sheaf F, then this is just a family like this, that family X that I said before, and we can compute the dimension of the family just with the formula that we already have, and this dimension is 7, which is too small to fill out an irreducible component of my modular space. Here I highlight that any reducible component in the modular space should have an expected dimension, which is 8 times the second Chern class minus, in this case, 5, and which in 7 is smaller than this quantity. But different from the case where the singularity of my sheaf does not meet the line, we also have the case when the singularity meets the line, and we have to find another way to compute the dimension of this family. We have to construct a family satisfying these properties and then compute the dimension of this family. And again, the dimension of this family is 7 by coincidence. This couldn't be another number. And again, this is too small to fill out an irreducible component of the modular space we are considering here. Then, indeed, we find when the degree of the support is 1, we find sheaves that can appear, but the family of these sheaves is too small to be a reducible component of my modular space. And now we go to the next possible number for the degree, which is 0. If the degree of my support is 0, then my sheaf is supported just in S points, and I have that the third Chern class is equal of my double dual is the third Chern class of my sheaf E plus 2S. But this is greater than C3 of E. But this will contradict the stability of my sheaf, because we will have that the third Chern class of the double dual is greater than the second Chern class square. And this cannot happen. The third Chern class should be always smaller or equal than C2 square. And indeed, this proves that the modular space of torsion-free sheaves, rank 2 torsion-free sheaves, Giesecke semistable, is isomorphic to the closure of my modular space of reflexive sheaves, and therefore this guy is reducible with dimension 11. This was also proved by Schmidt in 2019 using another techniques, independently by him. Okay, now we also have the result for second Chern class for third Chern class equals to 2. And now we'll have 2 reducible components. The first one will be the closure of the reflexive sheaves. And the new one appearing here is our component T of 0-dimensional singularity sheaves that will have dimension 15. And additionally, this modular space is connected. This is the more interesting information, I believe, here. I will give just an idea how to prove it. We know by our first result in this talk that the component T is a reducible component. And Cheng proved that, again, that this modular space of reflexive sheaves is reducible with dimension 11. Then the closure will be another reducible component in the modular space. And we can prove by inspection, more or less in the same that we just did for the case with third Chern class equals 4, that these are the only possible reducible components. And now I will give an idea how we can prove that this modular space is connected. So in order to do this, we consider a flat family of curves in P3 with base A1. That means we are taking a subscheme of P3 times A1, together with a projection, satisfying these following properties. For any point in A1 different from 0, I want my fiber to be a disjoint union of 2 lines. And in the 0th fiber, I want my Z0 scheme to be the union of 2 distinct lines meeting at one point, P, that I will call P. And I want this point to have, I didn't write it here, but I want this point to have, to be embedded. I want this point to be to have multiplicity 2. This means that for my scheme Z0, I will have an exact sequence of this form, OP, that goes inside the OZ0, that goes in the reduced, the structural sheaf of the reduced scheme. Okay, I just said that I can find this family. The clue for this is that both the schemes ZT and the scheme Z0 have the same genus and degree. Since we know that Hilbert scheme of curves is connected, we should be able to find a flat family like this. But indeed, we can actually make a flat family. We can build this morphism in order to prove that we have this deformation. So I'm not saying that just the degree and the genus to be the same in both cases is enough, but this should be a good indicative that we can find such family. I would denote by the ideal of my scheme Z, calligraphic Z, inside P3 times A1, to be my ideal sheaf of Z. And we can prove that it's possible to find a non-trivial extension of OP3 times A1 sheaves of my ideal sheaf, of the ideal of Z, to O minus 1 box times OA1, that will give me a family E in the middle. The important stuff here is that my sheaf E will be flat over A1, and by construction for any T inside A1, the restriction will give me a short exact sequence of this form appearing here for you, where my ET will be the restriction of my bold E to P3 times T. And this will give us a modular morphism from A1 to the modular space M-1 to 2 that will assign for each T my sheaf ET. The nice thing here is that we can check by diagram chasing that in the 0, the sheaf E0 is a sheaf inside that reducible component T minus 1 to 4 1. That is, it's a sheaf whose support is just 1 point. And for every T different from 0, we can prove that the sheaf appearing that exact sequence here is a reflexive sheaf in R minus 2, 2. That means that the geography of our modular space should be at least of this form. It should be a cross. Why I say should be at least is because we don't know if this phi0 that we proved that is in the intersection of the closure of R minus 1, 2, 2 is the only possible intersection. We can have more intersections, but we know that phi0 lie in the closure of R minus 1, 2, 2 and also lie in the components of these T components that I just defined. And additionally, we can also prove that the modular space minus 1 to 0 has exactly 4 reducible components. We can prove that these components are all rational. And additionally, we can prove that this guy is connected. This modular space with third Chern class equals 0 is of particular interest because it is the closure, is the compactification of the modular space of vector bundles on P3. And as you see, for smaller third Chern class, more complicated the modular space become. And I will not prove this theorem here. I will just make the geography of this guy here. So I have one component, which is the closure of the modular space of locally free sheaves. And I have two T components. That means that I have two components whose Kiwi is supported on zero-dimensional schemes. And I have one component X with dimension 11 these components whose QA is supported on OL, on a line, and possible points. And we know that these T components intersect the components of the vector bundles. And we know that the T2 component, one of the T components intersect my X components, but we do not know if the X components intersect with the component of the modular space of vector bundles. I also would like to add that the intersection of components with the components of purely torsion-free sheaves with the components with vector bundles is interesting to study this point of intersection, because in some sense we are studying those sheaves that can be desingularized. We can deform them in vector bundles, and then they will lose their singularities. So this is one of interests in studying this stuff. And the other interesting is because, well, we know a lot of stuff about the Hilbert scheme of curves, for instance, and we'd like to know a little bit more about this moduli space. With this, I believe I was a little too fast, but I finished my presentation here. And thank you and stay safe.
Okay, Charles, thank you. Let's thank the speaker. And okay, great, thanks. So are there any questions? Remember to turn on your microphone if you have questions.
Hi, may I ask a question? Are you listening me?
Yes, could you speak louder a bit? I can turn the volume.
Israel.
Okay, go ahead.
It's just a simple question. I mean, are there natural projective embeddings of these components? Where do they sit naturally?
We didn't check that. This is a good question, but we didn't check that. I mean, it would be interesting to know that, but we don't know. We do not know.
More questions?
I have a question.
Yes, go ahead, please.
Maybe it's a stupid question, I'm sorry, but you are constructing all your families through elementary transformations, right?
Yes.
How do you know that these are all the possibilities?
Okay, you say, for instance, in the case -1
you,
to 2.
You have torsion-free
yeah.
sheaves of Chern classes, and you're starting from reflexive sheaves, taking elementary transformation, and considering all the torsion sheaves, right? Torsion-free sheaves,
Yes.
sorry.
Yes. No, this is a good question.
How do you know you don't have other techniques?
No, it could be you could have another techniques to find reducible components, but in the case for small second Chern classes, in this case that I showed you, you will just have that component. And the way to prove it is by taking your hands in the dirt. You should start with a torsion-free sheaf, or either prove that it lies in one of you should prove that any torsion-free sheaf that you take, it's in the closure of the two that I said.
Okay,
you do it by,
you also proceed that it's torsion-free, it's constructed as a transformation you described.
Yes, yes, but only for a small second Chern class. We don't know if this is true for a greater one. You should, we indeed, in the case for M-1 to 2, I said, oh, these families are too small. Indeed, we make a deformation for the components in one of, from a sheaf in one of our components to that sheaf.
Okay. Thank you.
More questions? So I have a question, actually, which is in a sense similar to that of Simone's. If you pick a sheaf E, which is a general in its irreducible component, do you have any expectation for Q of E?
No.
Part of that, is there any bound on some?
No. The only thing that we know for a general sheaf is that you can see the slides?
Yes, yes.
Yeah, the only thing that is general for any sheaf is these three equalities here. Yeah, almost there. Just a minute. Yeah, the only thing that is general is these three equalities. You don't know anything more than that.
So even for general E, this QE could be very nasty. That is supported
Yes.
on curves of higher genus or have non-reduced points or these kind of
Yes.
things. Okay.
Yes, yes. And indeed, this is one of the main difficulties in proving that this guy is connected, right? Because the QE could be very, very nasty.
Okay. And another question that I had is, okay, you have this shift QE, its annihilator is the support of the singularities of E, right, where E fails to be locally free.
Yes.
But you can also use some fitting ideal for that. Are they the same?
I didn't thought about it, but yes. But if you use the fitting ideal, you may lose some information about the. You don't want to lose the information about the embedded points.
Right, yeah, the fitting ideal gives you the sub-scheme, not the sheaf on top of that. So I'm asking whether it's containing that information or not, or it's an extra information.
Okay, this is a good question. Yeah, I should verify this. Yes.
Okay.
Maybe yeah. If all the information is contained in the fitting ideal. Okay. I would think about it. Yeah,
The fitting ideal is related to a presentation of your sheaf.
Yes.
You think the other way around, right? Embed your sheaf in a reflexive one. So,
yeah. Okay.
Yeah, I don't know. I mean, I don't know. That.
Okay.
I'm just asking. Okay. All right. Any more questions? Okay. So let's thank Charles again. Then. Okay. So I should stop the recording, but I don't know how to do it. At some point it will work. But, well, let me thank all of you and say that next week we're going to have Jorge Vitório Pereira as the speaker, and the link will be announced soon. Okay, so thank you, Charles, for the talk, and thank you all for listening to it.
Thank you. Thank you for the opportunity.
Take care.
Bye.
Take care, everyone. Obrigado, Charles.
Valeu.
Tchau, tchau, gente. Obrigada, Charles.
Valeu. De nada. Tchau, tchau.
Falou, pessoal. Tchau, tchau.
Tchau. Tchau. Falou.